I don't forget it. Sure. Thank you. Next topic. Azeotropic mixtures or azeotropes. Azeotropic mixtures or azeotropes. If you remember, last time I taught you about positive and negative deviation from Raoult's law. First, let me explain. After that, I'll dictate you. I hope you remember this is the graph for solutions showing positive deviation. Now here we'll have to understand this topic, we need the definition of boiling point. What is boiling point? Boiling point is that temperature at which vapor pressure of the substance becomes equal to atmospheric pressure. Now, vapor pressure is increasing along y-axis. Let us say this horizontal line represents 760 millimeters of pressure, that is 1 atm pressure. If vapor pressure of solution becomes equal to 760 millimeters, this solution will start boiling. Now look here. At this composition, vapor pressure of the solution is this. It means to make the solution of this composition boil, I have to increase the vapor pressure by this amount. At this composition, vapor pressure is this much. If I want to make the solution boil with this composition, I have to increase vapor pressure to this extent. At this composition, vapor pressure of the solution is maximum. It means this gap is minimum. And if this gap is minimum, it means I have to supply minimum amount of energy to make this solution boil. Right? So this is one type of azeotrope, which is called minimum boiling azeotrope, because boiling point of the solution, which shows positive deviation, will be minimum at this composition. The other will be opposite. In case there is negative composition, then that composition, let me draw that one also, doesn't matter. This is the graph for negative deviation. When is this gap maximum? When this vapor pressure is minimum. At this composition, vapor pressure of the solution is minimum, means this gap is maximum. It means we have to supply maximum amount of energy to make it boil. So this solution, which shows negative deviation, at some intermediate composition, it has a minimum vapor pressure so that its boiling point is maximum. So this will be called maximum boiling azeotrope. See, if we have a mixture, if we have a solution of two liquids, and the solution is an ideal solution, when we distill this solution, out of those two components, that liquid whose boiling point is lower, that will distill first. After that, the second component whose boiling point is higher, that will start distilling off. But in case of azeotropes, both the components, they are so close friends of each other that both distill together. They do not leave each other. They distill together, even if they have a difference in their boiling point. Right? Now we start writing. Right. These are binary solutions of two liquids which have a fixed composition, in the liquid as well as vapor state, liquid as well as vapor state. They distill at a constant boiling point without any change in their composition. Components of an azeotrope cannot be separated from each other even by fractional distillation. As I told you, they are very close friends, and you might have observed two close friends generally move around together. So they do not leave each other, both distill together. They cannot be separated even by fractional distillation. They are of two types. Number one, minimum boiling azeotropes. Minimum boiling azeotropes. These are binary solutions of two liquids which show positive deviation from Raoult's law and have a maximum VP, maximum vapor pressure, at an intermediate composition whose boiling point, whose BP is minimum. For example, 95.5% ethanol plus 4.5% water. Number two, second, of course, will be opposite of the first. Number two, maximum boiling azeotropes. Maximum boiling azeotropes. These are binary solutions of two liquids which show negative deviation from Raoult's law and have a minimum vapor pressure at an intermediate composition whose boiling point is maximum. For example, 68% nitric acid plus 32% water. Next topic. See, so far we have been discussing about solutions in which both the components were liquids, ideal solution, non-ideal solutions, azeotropes, and they all had liquid components. Now, if there is some non-volatile solute added to the solvent, non-volatile means it will not change into vapors, then what will be the effect on vapor pressure of solvent? So write on the heading, effect of non-volatile solute on vapor pressure of solvent. It's a very, very small topic, but will be thoroughly used till the end of this chapter, right? Look at the board. Let us say this is a liquid solvent in a beaker or any vessel. How does evaporation take place? High energy liquid particle from the bulk moves in the upward direction, breaks forces of attraction from neighboring particles, and escapes in the form of vapor. This is also high energy particle breaks attractive forces from neighbors and goes into vapor state. Now, if we dissolve a non-volatile solute and prepare solution, these are non-volatile solute particles I've shown with the help of dots. Again, we consider evaporation of some high energy liquid particle. This will escape. This will escape. But this liquid particle, when moves in the upward direction, on the surface, it will come across a non-volatile solute particle. When it strikes non-volatile solute particle, it will not be able to escape. See, this escapes, this escapes, this escapes, but this does not escape because this is non-volatile solute particle. Due to this, what will happen? Number of particles in the vapor state will decrease, and therefore vapor pressure will decrease. So in simple words, we can say, if we dissolve a non-volatile solute in the solvent, vapor pressure of the solution will always be lower than the vapor pressure of pure solvent. Now, right, when a non-volatile, for non-volatile within brackets write on NV because you'll have to write many, many times in this chapter now. When a non-volatile solute is dissolved, okay, I'll repeat, when a non-volatile solute is dissolved, Anish, please switch over mic, please. Mic will disturb us. Yes, when a non-volatile solute is dissolved in a liquid solvent, from a solute particles present on the surface of solution act as obstacles for some solvent particles to escape in the form of vapors. Due to this, number of vapors formed decreases and VP decreases, vapor pressure decreases. Thus, VP of the solution containing a non-volatile solute is always lower than the VP of pure solvent. So particularly this last sentence we'll have to use a number of times. Next topic. Colligative properties. Colligative properties. Again, I'm just trying to save time. We'll have to write colligative properties many times. Please write CP and save time. Right, these are those properties of solutions which depend on the effective number. Underline these two words, effective number. Meaning of these two words, effective number, you'll be able to understand after 2 classes, right? So I'll repeat, are those properties of solutions which depend on the effective number of non-volatile NV solute particles irrespective of their nature. Irrespective of their nature. So as I said, effective number you'll not be able to understand for the time being. So if we skip these two words, for the time being, I can say colligative properties are those which depend on the number of non-volatile solute particles irrespective of their nature. Means whatever be the non-volatile solute, if number of solute particles in a particular amount of solvent, of course, is the same, then value of different colligative properties will also be same. Carry on. CPs are for those solutions only in which solute is non-volatile. So I'm emphasizing again, only for those solutions in which solute is non-volatile, we talk about these properties, that is colligative properties. These properties are, now form a list of these 4 properties. Then we take up these properties one by one. Number 1, relative lowering of vapor pressure. Relative lowering of vapor pressure. Number 2, elevation in boiling point. Number 3, depression in freezing point. And last is osmotic pressure. Osmotic pressure. So we start with the first colligative property, right on the heading. Number 1, relative lowering of vapor pressure. You'll have to copy from the board. We start with a sort of derivation, which is very, very simple. If you remember, I taught you about Raoult's law in the last class. And there I told you that total vapor pressure of the solution is partial vapor pressure of A plus partial vapor pressure of B. So we are starting with that. According to Raoult's law, PS or PT. PS means vapor pressure of solution. If we write PT, it means total vapor pressure. It's one and the same thing. So PS is equal to PA plus PB is equal to P naught A chi A plus 0. If you remember, I told you in this chapter, B will stand for solute. Solute in the present topic is non-volatile. And since B is non-volatile, it will not form vapors. Since it does not form vapors, it means partial vapor pressure of solute will be 0. Right? For the right on. Decrease in vapor pressure. Decrease in vapor pressure is equal to vapor pressure of pure solvent, that is P naught A, minus vapor pressure of solution, right? Because this vapor pressure of solution is nothing, just understand, vapor pressure of solution is nothing but partial vapor pressure of A. And partial vapor pressure of A has decreased because solute is non-volatile. I told you the last sentence will be used, obstacle, vapor pressure will decrease. So this is lowering of vapor pressure, and that will be equal to P naught A minus P naught A chi A. Right? This is vapor pressure of pure solvent, and this is vapor pressure of solvent in the solution, and its value is lower than the value of this. Now I can say this is P naught A into 1 minus chi A, or I can say P naught A chi B, right? Chi A plus chi B is 1. So 1 minus chi A is nothing but mole fraction of solute. This I can rearrange. This becomes P naught A minus PS divided by P naught A is equal to mole fraction of solute. Label this equation as equation 1A. Now, why did I label it a 1A? 1 means first colligative property. A means first equation of this colligative property. You'll be writing 4 equations for first colligative property, and this is first equation out of those 4. Now, whatever is the statement that will say in words, and that becomes the definition of Raoult's law. If you remember, we studied about definition of Raoult's law earlier. Earlier, both the components in the solution were volatile, liquid-liquid solution. But this time, when the solute is non-volatile, Raoult's law will have a different definition. Before I give you the definition, look at the board. Let us say there is a 50-mark test in the class, and one child scores 45. Teachers have the habit, either they write 45, but out of how much? Only the teacher knows or students know. And some have the habit, they will write maximum marks as denominator. If we only write 45, this is called marks obtained. And if we write 45 divided by 50, it means 45 marks obtained out of 50. Writing like this is called relative marking. Relative means comparative marking. Means compared to a maximum of 50, child has scored 45 marks. Now look here. This numerator is lowering of vapor pressure. And if we divide this lowering of vapor pressure with the maximum vapor pressure of pure solvent, then this entire expression will be called relative lowering of vapor pressure. So first of all, label accordingly. This numerator is lowering of Vp. And this entire left-hand side is relative lowering. Are you able to read? No. I'll write here. This entire is called relative lowering and the same I have to write in words, which becomes the second definition of Raoult's law. Now write down. On the basis of equation 1A, Raoult's law for solutions containing non-volatile solutes states that relative lowering of vapor pressure of solvent in the solution containing a non-volatile solute is equal to mole fraction of non-volatile solute. Now, on the basis of this equation, we'll solve one numerical. Check your WhatsApp message or chat box. I've shared one numerical. Numerical is vapor pressure of an aqueous solution containing 18 grams of glucose is 290 millimeters. Calculate mass of water in the solution. Vapor pressure of pure water is 300 millimeters. Number of moles of glucose will be 18 divided by molecular weight 0.1. I'm using equation 1a. P0A, vapor pressure of pure water 300 is given, minus PS, vapor pressure of solution 290 divided by P0 is equal to mole fraction of solute is number of moles of solute divided by number of moles of solute plus solvent, right? From this, calculate number of moles of water. This will come out to 2.9. It means 2.9 moles of water are present in the solution. Multiply by molecular weight, you'll get the mass of water. So this is 2.9 into 18, 52.2 grams of water is present in the solution. Now, we'll modify equation 1a. Although this modified form is rarely used, but I'll have to tell you that an equation 1a can be modified. Equation 1a can be modified as follows. As follows. Copy from the board, please. I'm writing equation 1a in the inverse form, right? So inverse of this equation will be P0A divided by P0A minus PS is equal to mole fraction of solute. This I'll write in the inverse form, Na plus Nb divided by Nb. This is nothing but 1 plus Na divided by Nb. Or I can say P0A divided by P0A minus PS minus 1 is equal to Na divided by Nb. I'll have to rub again and again because you'll not be able to read below this point, right? Now I'm writing above. So this is P0A minus P0A minus PS divided by P0A minus PS is equal to Na divided by Nb.
Sir, there will be plus PS in the numerator.
Sorry?
Sir, there will be plus PS in the numerator. The sign of PS will be positive in numerator.
Yes, yes. This is minus, so this becomes, it's okay now? Okay. Now I'll inverse it. Inverse. This becomes P0A minus PS divided by PS is equal to NB divided by Na. This is second equation of first colligative property. Therefore, I have numbered it as 1b. Although you can manage with 1a, this will rarely be used, rarely. Now imagine if there are two or more solutes present in the same solution. Then how do we use these two equations? How do we use equation 1a and 1b? In that case, both the equations will be modified. So further write down, if the solution contains two or more non-volatile solutes, then relative lowering of vapor pressure will be equal to the sum of mole fractions of all such non-volatile solutes. In that case, equation 1a is modified as follows. Earlier equation 1a was P0A minus PS upon P0A is equal to chi B, that is mole fraction of solute. But now if there are two or more than two non-volatile solutes, then it will be mole fraction of solute 1 plus mole fraction of solute 2 plus so on. It means right hand side now becomes sum of the mole fractions of all non-volatile solutes. Label this equation as 1C. Also, equation 1B will be modified as follows. P0A minus PS upon P0A, PS is equal to, earlier it was NB divided by NA, right? Now, I'll repeat, earlier it was NB divided by NA. And what is NB? Number of moles of non-volatile solute. Now in the numerator, we add number of moles of all non-volatile solutes. So it will be NB1 plus NB2 and so on, divided by number of moles of solvent. This becomes equation 1D. I'm sharing one numerical. In this, there are two solutes present in the same solution. We'll solve this numerical. Check your WhatsApp message. Yes, here it goes. And chat box of Zoom. Yes. Numerical is calculate lowering in vapor pressure of a solvent in an aqueous solution containing 18 grams of glucose, 12 grams of urea, and 174.6 grams of water. Vapor pressure of pure water is 400 millimeters. So first of all, number of moles of glucose, this is 18 grams. 18 divided by 180.1. Number of moles of urea, it is 12 grams. So 12 divided by 60, 0.2 mole. Number of moles of water, 174.6 divided by molecular weight, it will come out to 9.7 moles of water. important thing is, what do we have to calculate? We have to calculate lowering of vapor pressure. Neither we have to calculate vapor pressure of solution, nor we have to calculate relative lowering of vapor pressure. We in fact have to calculate the value of numerator. Numerator is lowering of vapor pressure. So it is P naught A minus PS. This will be the answer. Although we know the value of P naught A, but we need not substitute. Divided by P naught A. P naught A is given, but in the numerator we are not substituting, is equal to mole fraction of solute. Since they are two non-volatile solutes, we'll add their mole fractions. Mole fraction of glucose will be 0.1 divided by 10. Mole fraction of urea will be 0.2 divided by 10. Right? Mole fractions of solutes have been added, and this numerator will be the answer. This value will be 12 millimeters. Right? It's 0.3 divided by 10. Simple calculation. Further write down. If the solution is very dilute, write down, if the solution is very dilute, equation 1A can be modified as follows. So many modifications. Equation 1A can be modified as follows. Since solution is very dilute, it means in the denominator, I can neglect number of moles of solute compared to number of moles of solvent. So it becomes NB divided by Na. Remember, when you're solving the numerical, read the statement very, very carefully. Sometimes in the numerical itself, it's mentioned, we consider or assume that the solution is a dilute solution. Mentioning this means what? It means in the denominator, you should neglect number of moles of solute so that calculations become easy. So this is equal to number of moles of solute will be weight of solute divided by molecular weight. Number of moles of solvent will be weight of solvent divided by molecular weight of solvent. Further write down. For a particular amount of solvent, it becomes, now, will you be able to read? Yes. When I say for a particular amount of solvent, it means we fix the quantity of solvent. This much is the quantity of solvent. We fix it. Now look here. Molecular weights are constants. And when I say for a particular amount of solvent, it means weight of solvent is also constant. And if these three are constant, it means I can replace these three by the sign of proportionality. So it becomes, write down, P naught A minus PS upon P naught A directly proportional to weight of non-volatile solute. And weight of anything is directly proportional to number of particles of that substance. So I can say directly proportional to number of solute particles. So what we have at the end now, if we read in words, I can say relative lowering of vapor pressure is directly proportional to number of non-volatile solute particles. And that's what is the definition of colligative properties, right? If you remember, I defined colligative properties as said colligative properties are those which depend on the number of non-volatile solute particles, right? Effective we'll use later on. So this value, relative lowering of vapor pressure, depends on the number of solute particles. This proves that relative lowering of VP, relative lowering of vapor pressure, is a colligative property. So we have finished one colligative property. We'll start second colligative property. Maybe a small part of it we'll be able to cover today. Mathematical part, of course, we'll have to take up in the next class. Right on. Number 2, elevation in boiling point. Elevation in boiling point. First, write the definition of boiling point, which will be used to understand this topic. Right on. Boiling point of a substance, BP of a substance, is that temperature at which vapor pressure becomes equal to atmospheric pressure. Becomes equal to atmospheric pressure. Now, before I take up this topic properly, this particular topic, let us use this definition for something else. See, if we try, you know, cooking medium is water. Cooking is always done in water. If we put vegetables in water and try to cook in an open vessel, water will boil at 100 degrees centigrade in the open vessel. It means vegetables will also be heated to 100 degrees centigrade in that open vessel. And cooking takes a certain time. If we try to do this cooking experiment at high altitude, hill station, at high altitude, atmospheric pressure is low. And if atmospheric pressure is low, then according to definition of boiling point of water will also be lower than 100 degrees centigrade. Let us say at high altitude on a hill station, water boils at 100 degrees centigrade. It means in that open vessel, vegetables will also get a maximum of 95 degrees centigrade temperature. And since vegetables do not get 100 degrees centigrade temperature, they get a lower temperature, cooking will take longer time. Remember, water will boil early compared to plains. Water will boil early. This will boil at 95 degrees centigrade. But cooking will take longer time. On the other hand, cooking, is faster in a pressure cooker. Why is it faster in a pressure cooker? Because in the pressure cooker, boiling point of water is elevated. Prakhar, you want to ask something?
No, sir.
Mic on it. Achha. Why does water boil at a high temperature in a pressure cooker? The reason is pressure cooker is a closed vessel. When we heat, vapors are formed. Those vapors do not escape into the atmosphere. If the pressure is very high, then only vapors will escape. Otherwise, vapors will keep on accumulating inside the pressure cooker so that pressure on the surface of liquid water will keep on increasing. As pressure on the surface of liquid water keeps on increasing, it means boiling point of water keeps on increasing. So remember, water boils at a very high temperature inside the pressure cooker. That is why vegetables also get very high temperature. And this is the reason cooking is fast in a pressure cooker. Chaliye. Now we come back to our topic. You have written the definition of boiling point. Right on next paragraph. When a non-volatile solute is dissolved in a solvent, its boiling point increases. Reason for the elevation in boiling point is given below. Reason for the elevation in boiling point is given below. Look at the board. I'm explaining why does the boiling point increase on addition of non-volatile solute. Understand this, then I'll dictate you. Let us say at a particular temperature, we have water, its vapor pressure is 300 millimeters. If I want to make it boil, I have to increase its vapor pressure to 760 millimeters. And to increase vapor pressure from 300 to 760, I have to supply certain amount of energy. Now, at the same temperature, if I dissolve some non-volatile solute, let us say I dissolve sodium chloride, vapor pressure will decrease, right? Let us say vapor pressure becomes 250 millimeters. When vapor pressure decreases, it means this gap increases. And when this gap increases, it means now I'll have to supply more amount of energy to make it boil. If I add some more non-volatile solute, more solute means more obstacles. So vapor pressure will further decrease 200 millimeters. This gap will further increase. It means boiling point will further increase. This you can even try at home. Take some water in an open vessel, boil it. When it starts boiling, add some sugar to it and watch immediately. After adding sugar or sodium chloride, immediately watch it. You'll find that it stops boiling for a while. Reason is this reason. Now, pure water boils at 100 degrees centigrade. That is at 100 degrees centigrade, Vp of pure water is 760 millimeters. 760 millimeters. At this temperature, when some non-volatile solute is dissolved in water, its vapor pressure falls below 760 millimeters and it stops boiling. To make its vapor pressure equal to 760 millimeters, that is, to make it boil again, temperature has to be increased above 100 degrees centigrade. That is, boiling point is elevated. We'll take just 5 more minutes. We'll finish one graph. Right on next paragraph. Graphically, variation of vapor pressure with temperature and concentration of solution and its effect on boiling point is given below. Please keep on drawing, keep on understanding, but I'll simultaneously explain as well. Along y-axis is vapor pressure, along x-axis is temperature, and this is atmospheric pressure, that is 760 millimeters. So when vapor pressure becomes equal to 760, the substance will start boiling. Please understand and draw. Look here. Let us say we have a pure solvent at this temperature, and let us say its vapor pressure is this much, represented by this point. When we increase temperature, vapor pressure will increase. So we keep on increasing the temperature, vapor pressure will keep on increasing. At this temperature, vapor pressure becomes equal to atmospheric pressure. It means this temperature is boiling point of the solvent. So this graph is for the solvent. This is BP of solvent, boiling point of solvent. I hope it's visible now. Boiling point of solvent. Now we go back to the original temperature. Let us say I dissolve some non-volatile solute and prepare a solution. When solute is dissolved, vapor pressure will decrease. Let us say vapor pressure becomes this much. Now, when I increase the temperature, vapor pressure of the solution will increase. But at any temperature, due to the presence of non-volatile solute, vapor pressure will always remain lower, remain lesser than the vapor pressure of solvent. It means the graph will be parallel to this graph. It means this is the graph for solution number 1. This solution boils at a higher temperature. So this is BP of solution 1. This difference in boiling points, this is called elevation in boiling point. Symbol is delta TB. So this is elevation in boiling point of solution 1. Again, back to the same temperature. If I add some more non-volatile solute, vapor pressure will further decrease. I again increase temperature, vapor pressure will increase. All the three graphs will be parallel to each other. This will boil at a still higher temperature. This is BP of solution number 2. This is graph for solution number 2. And this bigger gap, this is delta TB of solution number 2. So we conclude one thing and then wind up today's class. So conclusion is, if concentration of the solution is high, elevation in boiling point of solution is also higher. This elevation is lower, small gap. This elevation has a larger value. So concentration increases, value of elevation in boiling point, will also increase. So I can say delta TB is directly proportional to concentration of the solution. We'll start the next class with this note, with this conclusion only. Right? Please keep on working hard. I'm constantly sharing MCQs, solve them. Really, some of them are very easy. If you have a feeling such simple numericals MCQs will not be asked, certainly will not be asked. But I have observed in the past, even in JEE Mains, sometimes very simple MCQs are asked. And you'll have the feeling, hey, what's this? Is this a question of JEE Mains standard? But at the same time, some difficult questions are also asked. So you'll have a mixture of simple and difficult questions in MCQs. For this chapter, I'll be sharing 200 plus MCQs. In case you are not able to understand, you are not able to get the proper answer, you can ask me. I'll share the solution for that particular question. And that will not be shared in the group. I'll personally message you the solution, or you can call me, I'll explain. Right? Right, children? You can log out. Bye.
Yes, sir.
Thank you,
Bye.
sir.
Thank you, sir.
Bye, sir.
Thank you, sir.
Thank you, sir.